The thunder of 4 Mamoru engines shatters the still morning air as Japan's first heavy bomber, the Nakajima Shinzō, lurches down the concrete runway. At more than 44,000 pounds empty, it outweighs America's B-17 Flying Fortress by nearly 8,000. The test pilot grips the yoke, fighting sluggish controls as the massive aircraft claws into the sky, climbing barely 500 feet per minute, half the pace of its American rival. Below, Chief Engineer Kenichi Matsumura lowers his binoculars, his notebook packed with equations that suddenly mean nothing. 2 years earlier, Japan had bought a single Douglas DC-4E from the United States, believing they had purchased the very secret of American air power. For years, they dismantled it, measured it, copied every bolt, every rivet, every system. But as the Shinzō vanishes into the haze, struggling to stay aloft, Matsumura realizes a devastating truth. You can imitate another nation's machines, but not the mindset that built them. The morning sun stretched long golden shadows across Oda Airfield as Chief Engineer Kenichi Matsumura reset his stopwatch, ready to witness what the Imperial Japanese Navy believed would redefine their nation's air power. It was April 8, 1941. At the far end of the runway stood a machine that embodied both pride and desperation, the Nakajima G5N Shinzō, Japan's first heavy bomber. It sat gleaming like a metal fortress, its massive frame trembling as 4 Mamoru engines rumbled to life, their deep throaty growl echoing through the hangars and up into the hills. For 18 relentless months, Matsumura had lived inside this project. Every bolt, every electrical line, every vibration of its frame bore his signature. This was to be Japan's answer to the American Flying Fortress. The Navy had promised it would change the course of the coming war, a weapon capable of striking at the industrial heart of an enemy 2,000 miles away. The Americans possessed what Japan's strategists envied most, the ability to deliver destruction across oceans. Their Boeing B-17 Flying Fortress had become a symbol of industrial confidence, a machine built to endure punishing missions and return home again. Japan wanted that same capability, the power to carry the war far beyond its shores. But as Matsumura watched the Shinzō from the runway, clipboard in hand, he wondered if they had reached too far. Major Katsuaki Kira, the Navy's most seasoned test pilot, climbed into the cockpit. The Shinzō stretched nearly 140 feet from nose to tail, its polished aluminum skin flashing under the early sun. On paper, its specifications promised excellence: a 4,000-kilogram bomb load, 3,500 miles of range, and enough defensive turrets to hold off attacking fighters. The Navy procurement officers had already declared it Japan's war winner, the bomber that would bring American industry to its knees. But Matsumura's engineering notes painted a darker picture. His calculations had been bothering him for weeks. The empty weight, 44,313 pounds, exceeded even the heaviest American bombers. By comparison, the U.S. Army's B-17G weighed only 3,635 pounds in the same configuration. The Japanese aircraft was almost 8,000 pounds heavier, without offering a single advantage. To a man trained in aeronautical design, that difference wasn't minor. It was catastrophic. As the engines reached full power, the sound rolled like thunder across the field. Each Mamoru radial produced 1,870 horsepower, combining for 7,480 total. Enough, in theory, to lift 62,000 pounds of steel, fuel, and ambition. Matsumura's mind did the math automatically. 120 horsepower per 1,000 pounds. The American B-17 achieved 133, and those Wright Cyclone engines had already earned a reputation for reliability, the kind of mechanical trust only mass production and battlefield experience could provide. Major Kira released the brakes. The Shinzō began its takeoff roll, slow and deliberate. The massive propellers bit into the air as the bomber gathered speed. 1,000 feet, then 2, then 3. The stopwatch in Matsumura's hand ticked mercilessly. The aircraft consumed more than 4,000 feet of runway before its nose finally lifted. A B-17 under similar weight needed barely half that distance. The Shinzō left the ground reluctantly, climbing at a crawl, 500 feet per minute, no more. Through his binoculars, Matsumura watched as Kira wrestled the controls, the plane responding with sluggish, oily resistance. Every adjustment required effort. The bomber didn't so much fly as it labored through the sky. American pilots often described their fortresses as eager to climb, eager to fight gravity. The Shinzō looked tired before the mission had even begun. Within minutes, the aircraft disappeared into the morning haze, struggling to maintain altitude. Matsumura lowered his binoculars. The weight of realization settled in. Japan's most ambitious aviation project was a failure in motion. The roots of that failure traced back 2 years. In 1939, Japanese negotiators had proudly acquired the only existing Douglas DC-4E prototype from the United States for $275,000, a staggering sum in those days. Tokyo's engineers were convinced they had obtained the master key to America's aviation supremacy. The DC-4E had seemed perfect, an enormous all-metal airliner with 4 engines, tricycle landing gear, and a wingspan of 138 feet. But what Japan didn't realize was that America had already discarded it. The DC-4E had been rejected by every major U.S. airline, American, United, and Eastern. Each had found it too complex, too heavy, and too costly to operate. What Japan believed was a marvel of innovation was, in truth, a technological dead. American industry's most expensive lesson. Matsumura's team had spent months disassembling the aircraft, blueprinting every wire and bracket. They assumed that American design philosophy favored brute strength and over-engineering. So, they strengthened it even further, adding extra frames, reinforcing spars, and installing additional gun turrets to satisfy the Navy's demand for protection. In doing so, they turned an already overweight civilian design into a military giant that could barely lift itself. The Shinzō's engines, Japan's proud Mamoru radials, were another problem. On paper, they matched the output of the American Wright Cyclones. In practice, they failed constantly. Each required a full overhaul after just 50 flight hours. The American engines, by contrast, ran nearly 400 hours between major maintenance cycles. Every repair consumed scarce metals and skilled manpower, resources Japan could ill afford. The irony was brutal. Japan had invested 2 years and millions of yen to copy an airplane the Americans had already abandoned, and then made it heavier, slower, and more fragile in the process. The Shinzō was, in essence, a perfect reproduction of failure. Every line in Matsumura's notebooks confirmed what the morning's flight now proved. The bomber's balance was wrong. Its weight distribution crippled lift. Its engines strained near maximum output just to stay airborne. The Shinzō wasn't a war winner. It was a monument to misunderstanding, a flawless execution of a flawed concept. 20 minutes after takeoff, the control tower's radio crackled. Major Kira's voice came through, steady but tense, reporting level flight at low altitude. Further ceiling tests would follow, but Matsumura already knew the truth. The aircraft would never reach its intended combat ceiling. Under real operational weight, it would struggle to pass 24,000 feet. By comparison, American B-17s routinely flew between 25 and 30,000 feet. That altitude made them nearly untouchable to most Japanese interceptors. American bombers used the sky itself as armor. Japan's aircraft, forced to fly lower and slower, would always be targets rather than hunters. As the test flight continued, Matsumura left the runway and began walking toward the hangars. His steps were slow, his mind already racing through the implications. The Shinzō had been Japan's great hope, proof that with enough determination they could match American industry. But what the morning had revealed was a sobering truth. Japan's engineers had built a machine of immense precision on the wrong foundation. The failure wasn't in the craftsmanship, it was in the philosophy. The DC-4E purchase had been made on the assumption that technology could be transferred, like property, that by owning the blueprint, one could inherit the genius behind it. But genius cannot be reverse engineered. American aircraft designers didn't simply build airplanes. They built systems, machines designed for mass production, field maintenance, and endurance under combat conditions. Every component of a B-17 could be replaced by a mechanic with minimal training. Every rivet and panel was standardized, designed for volume and reliability. Japan's engineers, by contrast, built art. Their machines were masterpieces of individual craftsmanship, complex, beautiful, and fragile. They demanded attention from highly skilled hands and constant maintenance that war could not afford. That difference, philosophy over design, was what separated industrial warfare from artisanal ambition. Radio chatter broke through the quiet again as Kira prepared to descend. The bomber circled back toward the airfield, engines straining audibly as it lined up for landing. To the observers in the control tower, the test seemed successful enough. The aircraft had flown after all. But Matsumura knew better. The numbers in his head didn't lie. The climb rate, fuel consumption, and stress readings meant only one thing. The Shinzo would never see combat service. It was too heavy, too fragile, too demanding. Even if it could be built in quantity, which it couldn't, the Navy had no logistics system capable of supporting such a temperamental machine in wartime. As the bomber touched down and rolled to a halt, the engines coughed in protest before falling silent. A thin line of smoke drifted from one of the exhaust stacks. To the untrained eye, it looked like a routine test. To Matsumura, it was the visible proof of a dream collapsing. Japan had tried to copy America's might, but imitation without understanding is only mimicry. The Americans built planes to win wars. Japan had built a machine that could never survive one. Still, Matsumura felt no bitterness. Failure, he realized, was its own kind of teacher. The Shinzo might never bomb enemy factories, but its lesson would echo across Japan's engineering circles. To build a weapon of power, one must first understand the mindset that forged it. That morning, as he walked back across the field with the echo of engines fading behind him, Matsumura knew Japan's aviation dream had reached its limit, not in courage or skill, but in the invisible walls of philosophy and industry. And in that quiet realization, history had already begun to turn. Spring arrived at Nakajima's Kizumi facility under strict new orders from Imperial Navy headquarters. Despite the Shinzān's disappointing test results, Tokyo remained convinced that Japan's heavy bomber program could still alter the course of the war. Admiral Isoroku Yamamoto's staff, operating with a sense of growing urgency, issued a directive that many engineers considered impossible. Develop a bomber capable of striking the American mainland within 18 months, or watch Japan's strategic advantage vanish entirely. The program entered its most demanding phase. Kenichi Matsumura oversaw an expanded engineering corps of more than 200 specialists drawn from every major aircraft project in the country. Production bays that once assembled fighters now echoed with the sound of heavy machining as Japan's best designers labored to refine the nation's first four-engine strategic aircraft. Official documents continue to describe the Shinzān in language of triumph. Procurement papers listed an impressive set of figures: a bomb load of 4,000 kilograms, operational range of 3,500 miles, defensive armament of 4 20mm cannons, and 12 7.7mm machine guns. On paper, the aircraft appeared capable of delivering destruction to industrial targets as far as California. Flight test data told a less optimistic story. The prototype's maximum speed of just over 260 miles per hour left it vulnerable to modern interceptors, while a service ceiling below 25,000 feet meant enemy fighters could attack freely from above. Intelligence reports on American P-38 Lightnings confirmed that the United States now possessed aircraft capable of climbing to nearly 39,000 feet and diving at speeds in excess of 400 miles per hour, performance figures the Shinzān could not approach. The situation worsened with every flight hour logged. Engine reliability, already a major concern, deteriorated into a critical flaw. Each Mamoru radial required a complete overhaul after only 50 hours of operation, consuming precious quantities of aluminum alloy that Japan's industry could scarcely supply. The engines demanded highly skilled machinists for assembly and maintenance, the same workers urgently needed for Zero fighter production as the Pacific front widened. Vibrations from the massive power plants caused severe structural fatigue, loosening instruments, cracking fuel lines, and stressing wing spars beyond tolerance. By comparison, captured Wright Cyclone engines from downed American B-17s showed endurance approaching 400 hours between major maintenance intervals. U.S. engineers had accepted modest power output in exchange for long-term reliability, a design trade-off that produced consistent mission readiness. Japanese philosophy favored peak performance, but the result was mechanical fragility. American bomber squadrons could sustain continuous operations for months. Japan's prototype spent more time in overhaul bays than in the air. Matsumura's team conducted detailed examinations of the Wright R-1820 engines recovered from aircraft shot down over the Philippines. The findings were sobering. American cooling fins were simple in design and produced through automated milling processes, while Japanese versions required intricate hand finishing by expert craftsmen. U.S. connecting rods were forged from standardized alloys suited for large-scale manufacture. Japanese rods relied on limited exotic metals that introduced severe supply constraints. Every comparison highlighted the same fundamental divide. American aircraft were designed from inception for mass production. Japanese aircraft were designed for precision craftsmanship. That distinction reached beyond individual components. In the United States, assembly lines were built around standardized jigs and repetitive processes, allowing minimally trained workers to construct complex machines in predictable timeframes. In Japan, each major component demanded expert adjustment, custom fitting, and manual alignment. The result was an aircraft that demonstrated technical excellence in isolated tests, but deteriorated quickly under field conditions. Maintenance required the same level of skill as initial construction, creating an unsustainable operational burden as the war expanded. By mid-1941, the Shinzān program had absorbed resources equivalent to those needed to build 300 fighter aircraft, yet yielded only 6 complete prototypes. Production rates deemed sufficient during pre-war planning proved catastrophically inadequate under wartime conditions. Meanwhile, American factories were producing B-17s at rates exceeding 20 aircraft per month from individual assembly lines, with additional facilities scheduled to double that output as contracts increased. Weight growth remained the most persistent engineering problem. Each improvement intended to enhance survivability added further mass. Armor plating for critical areas increased empty weight by more than half a ton. Revised defensive gun installations added nearly another. The introduction of self-sealing fuel tanks essential for operations over hostile territory added over 2,500 pounds. Every addition eroded climb rate, range, and service ceiling, forcing engineers into a cycle where each attempt to correct one weakness amplified another. Performance projections revealed that a fully loaded Shinzān could not maintain safe altitude if one engine failed. Twin-engine operation, a condition frequently encountered in combat for American bombers, proved barely controllable. A single-engine failure during takeoff often resulted in aborted flights or near disasters. Reports from Europe indicated that B-17 crews regularly returned home on 2 functioning engines, sometimes even 1, a level of resilience the Shinzān could never replicate. The material crisis that began to affect Japan's entire aviation industry in late 1941 struck the heavy bomber program with particular force. Each Shinzān required approximately 8 tons of aluminum alloy, enough to build multiple fighters or several medium bombers. National production capacity could theoretically support a dozen heavy bombers per month, but only if all other aircraft programs were halted. In practice, priority shifted toward defending the home islands, and fighter production absorbed nearly all available metal. Intelligence estimates placed American aluminum output at over 900,000 tons annually by 1943. Japanese production never exceeded 142,000 tons. The disparity rendered large-scale strategic bomber construction impossible regardless of technical progress. Industrial limitations extended into manufacturing infrastructure. American plants benefited from vast machine tool inventories and extensive subcontract networks. Japan's facilities, though capable of fine craftsmanship, lacked sufficient automation and standardized tooling to produce large assemblies rapidly. Each fuselage section, wing spar, and engine mount required hand fitting. Bottlenecks multiplied, and delivery schedules slipped month after month. As resources tightened, morale within the design bureau began to erode. Engineers who had dedicated years to perfecting components saw their efforts nullified by systemic deficiencies beyond their control. Test pilots filed increasingly pessimistic reports. Structural fatigue appeared after as few as 20 hours. A flight. Hydraulic systems exhibited leaks caused by vibration resonance. Electrical wiring, rerouted repeatedly to accommodate design modifications, became a maintenance hazard. The bomber's complexity now exceeded the operational capabilities of Japan's ground crews. By summer's end, it was evident that the Shinzān program could not meet its objectives. Only a handful of airframes had been completed, and each required extensive maintenance after every test flight. The theoretical combat range of 3,500 miles, calculated under ideal laboratory conditions, proved unattainable with full bomb loads and operational fuel reserves. Even if the aircraft had achieved its projected specifications, the inability to produce them in meaningful numbers eliminated any strategic relevance. The Navy's procurement offices continued to issue optimistic statements to maintain public and political confidence. Reports emphasized incremental improvements and downplayed recurring failures. Within the technical divisions, however, the conclusion was clear. Japan's heavy bomber effort was constrained not by engineering ignorance, but by industrial incapacity. The country possessed the intellectual resources to design competitive aircraft, but lacked the mass production systems to sustain them. Captured American bombers provided daily evidence of that divide. Inspections revealed design philosophies centered on ease of manufacture and field maintenance. Wiring harnesses were color-coded for quick identification. Panels could be removed with standardized fasteners accessible by simple tools. Major components were interchangeable between aircraft. Japanese designs required custom alignment and adjustment at nearly every stage. The differences were small individually, but decisive in aggregate. By autumn, the Shinzān's limitations were beyond dispute. Its operational ceiling placed it within range of every Allied interceptor. Its climb rate remained insufficient for tactical flexibility. Maintenance demands consumed scarce labor. Aluminum shortages slowed even prototype construction. Each successive test flight confirmed the same reality. Japan's first heavy bomber was a technical achievement that could not translate into practical warfare. The project persisted through bureaucratic momentum rather than engineering promise. While official memoranda continued to list new modifications and performance goals, production tooling quietly shifted back to fighter manufacture. The Shinzān would remain a footnote in Japan's wartime aviation history, a symbol of ambition, constrained by industrial reality. In March 1942, a flatbed convoy rolled through the gates of Nakajima's main engineering complex, carrying what the Imperial Navy considered its most valuable prize, a captured American B-17E Flying Fortress. The bomber had been forced down in the Philippines after sustaining heavy fighter damage, its fuselage scorched and punctured, but largely intact. To Kenichi Matsumura and his team of engineers, it represented an unprecedented opportunity. For the first time, Japan's aviation industry could examine a complete example of the aircraft that had defined American strategic air power. The bomber appeared smaller than anticipated. Its 103-foot wingspan gave it a compact, purposeful look beside the massive 138-foot Shinzān prototypes parked nearby. Yet, as technicians maneuvered the aircraft into the hangar and began their inspection, the differences in philosophy and execution became unmistakable. Where the Shinzān embodied craftsmanship, the B-17 reflected systematized efficiency. Its surfaces showed no evidence of individual fitting or hand finishing, only the uniform precision of mass production. Measurements confirmed what engineers had long suspected. The B-17's empty weight was just over 36,000 pounds, roughly 8,000 pounds lighter than the Japanese bomber, despite similar armament, range, and payload. Matsumura personally supervised the disassembly of the aircraft, beginning with the engines. The four Wright R-1820 Cyclone radials, each weighing about 1,850 pounds, delivered 1,200 horsepower at takeoff. By comparison, Japan's Mamoru engines, produced nearly 1,900 horsepower, but weighed 2,100 pounds each, a seemingly small difference that multiplied across 4 power plants to create major penalties in performance and reliability. When the American engines were opened for inspection, the findings were startling. After hundreds of flight hours, cylinder walls remained evenly scored, bearings intact, and cooling fins unwarped despite clear signs of combat stress. The simplicity of the design defied Japanese expectations. Straight-cut cooling fins and standardized fittings indicated a system built for industrial reproduction, not perfection. Manufacturing tolerances were broader than Japanese norms, yet operational consistency was higher. The Americans had chosen to prioritize repeatable performance and ease of maintenance over precision for its own sake. Airframe construction offered similar revelations. The B-17's wing spars were made from aluminum extrusions reinforced only where stress analysis demanded it. Every rib and joint followed a logic of minimum material for maximum strength. The Shinzān's wings, by contrast, relied on individually machined forgings, intricate and beautifully crafted, but slow to produce and impossible to standardize. Each part demanded hours of skilled labor that Japan's limited industrial base could not sustain. Electrical and mechanical systems further illustrated the divide. The B-17's wiring harnesses were color-coded and connected by standardized plugs. Circuits were routed through accessible panels, allowing quick inspection and replacement. The Shinzān systems used custom connectors and hidden routing paths that required specialized knowledge to service. Field maintenance on the Japanese bomber often took days. Equivalent work on the American aircraft could be completed within hours by general mechanics. The differences in armament installation were equally striking. American gun mounts were modular, designed for rapid removal or interchange between weapon types. Ammunition feeds were simple mechanical designs that rarely jammed even under extreme maneuvering. Japanese engineers, in pursuit of precision, had developed hydraulically assisted turrets that offered greater theoretical accuracy, but required constant calibration by expert armorers. The result was an aircraft more delicate than durable, a machine unsuited to sustained field operations. Flight control systems revealed perhaps the most profound divergence in design philosophy. The B-17 relied on cable and pulley linkages, mechanically basic but highly reliable. Japanese designers had favored hydraulic assist systems, believing them more advanced. Yet pilot reports from both sides told a different story. The Fortress's direct feedback controls provided tactile warning of stall conditions, enhancing safety. Hydraulic systems, while smooth, masked critical aerodynamic cues, increasing the risk of unrecoverable stalls. What the Americans called simplicity, Japanese engineers had dismissed as primitive. In truth, it reflected an understanding of operational necessity. Fuel systems provided another point of contrast. The B-17's tanks consisted of simple aluminum shells lined with replaceable rubber bladders. Self-sealing protection came from layers of treated rubber that closed punctures automatically, a solution that required minimal machinery and allowed rapid field replacement. The Shinzān's fuel system, by contrast, used intricate pumps and precision valves that performed flawlessly in laboratory conditions but failed unpredictably under combat stress. Each additional refinement created a new vulnerability. By the summer of 1942, the captured fortress had been completely disassembled, catalogued, and analyzed. The data compiled by Matsumura's team filled volumes. Every measurement reinforced a single conclusion. American superiority did not originate from technology alone, but from an industrial philosophy Japan had never fully grasped. U.S. engineers had not designed an aircraft. They had designed a production system. Each component, every bracket, and all wiring were optimized not for craftsmanship, but for mass manufacture, maintenance, and standardized replacement. The production statistics underscored this philosophy. Boeing's Seattle plant was turning out 48 flying fortresses every month, with parallel assembly lines under construction in Wichita and Long Beach. Each bomber required roughly 15,000 man-hours to complete. The Shinzān prototypes, hand-built at Nakajima, consumed more than 32,000 man-hours each. In practical terms, American workers could build 3 operational bombers in the time it took Japanese artisans to finish one prototype. Material efficiency told a similar story. The B-17 used about 5.2 tons of aluminum alloy per airframe. The Shinzān required over 8 tons to deliver comparable range and payload. The difference stemmed from fundamental engineering approach. American designers had mapped stress loads and eliminated all unnecessary material. Japanese engineers had simply reinforced every structure for safety, adding weight that reduced performance without increasing durability. Maintenance doctrine provided further evidence of systemic divergence. Recovered logbooks from the captured aircraft detailed a regimented schedule of standardized upkeep. Engine swaps could be completed in 6 hours using common tools. Hydraulic repairs required no specialized training. Every step was documented in technical manuals accessible to any qualified crew chief. Japanese bombers required expert supervision even for routine tasks. No 2 aircraft were identical enough to permit standard procedures. Battle damage repair. Techniques demonstrated the same pragmatic ingenuity. The B-17 structure was deliberately designed to fail in predictable ways. Damage localized around specific joints or panels that could be replaced in the field. Spare aluminum sheet and angle stock were sufficient to return an aircraft to service within days. Japanese designs demanded custom-machined replacement parts. A single damaged section could render an aircraft unserviceable for weeks. What the Americans called good enough kept their fleets flying. What Japan called perfect kept theirs grounded. The cumulative effect of these discoveries forced a reassessment within the Navy's technical divisions. Japan's engineers were no longer simply competing against American machines. They were confronting an industrial system capable of producing, maintaining, and replacing those machines at a rate Japan could never match. It was not a matter of innovation or skill. It was a matter of scale, process, and philosophy. By October 1942, Matsumura's team had completed their final comparative analysis. The conclusion was unambiguous. The B-17's superiority lay not in its materials or advanced features, but in the clarity of its design objective. American engineers had solved the correct problem: how to create a complex combat aircraft that ordinary workers could build, maintain, and repair under wartime conditions. Japan had pursued refinement. America had pursued reproducibility. The difference defined the war's industrial balance. Official reports recommended a complete redesign of Japan's heavy bomber program based on American production principles: standardized components, simplified systems, and modular construction. But the recommendation came too late. By late 1942, the Pacific War had entered a phase that left no room for such fundamental transformation. Japan's aviation industry remained locked into methods optimized for precision rather than scale. The Shinzān project, already plagued by material shortages and performance shortfalls, could not be saved by philosophy alone. The captured B-17 was eventually dismantled completely, its components distributed among research institutes for study. Its lessons, however, remained clear. The machine that arrived on a flatbed truck in the spring of 1942 had done more than reveal the secrets of American aviation. It had exposed the limits of Japan's industrial imagination. The telegram from Imperial Navy headquarters arrived at Nakajima's Kusumi facility on a humid morning in mid-September 1943. Stamped with the red insignia of the Navy's Air Technical Department, it carried specifications that seemed less like engineering requirements and more like an act of desperation. Kenichi Matsumura read the document twice in silence. Then, placing it flat on his drafting table, he exhaled slowly. The numbers in front of him were audacious, bordering on impossible. A maximum speed of 370 miles per hour, faster than any heavy bomber in existence. A service ceiling of 33,000 feet, higher than most interceptor aircraft could reach. A combat radius of 4,600 miles, enough to strike targets on the American mainland and return. A bomb load of 800 pounds capable of destroying industrial centers in a single sortie. It was, Matsumura realized, a fantasy written by men who had never touched an airframe or calculated a power-to-weight ratio. But the Imperial Navy wasn't asking for debate. They were ordering a miracle. For 18 months, Nakajima engineers had studied the captured B-17 flying fortress, dismantling its engines and airframe bolt by bolt, discovering principles of design that contradicted everything Japanese engineers had believed. The revelation had been simple yet profound. The Americans were not building airplanes. They were building systems of production. Matsumura had watched with awe as his engineers documented every difference. The way American aircraft used standardized components, looser tolerances, simplified wiring, and replaceable parts. What the Japanese had mistaken for crudeness was, in fact, industrial genius. Now, in 1943, Japan faced the ultimate test, to apply those lessons in a war already slipping beyond its reach. The new project was designated G8N Renzān, Mountain Range. It would abandon every principle that had defined Japanese aircraft development since the 1930s. No more handcrafted perfection. No more over-engineered components. For the first time, Japan would design an aircraft not to impress engineers, but to serve soldiers, built for production, maintainability, and endurance. Through the autumn of 1943, Matsumura's drafting, rooms burned with light long past midnight. Teams of engineers crowded around blueprints, erasing old assumptions and drawing new possibilities. Every component of the Shinzāns, Japan's earlier heavy bomber, was reconsidered, simplified, or discarded. The new Renzān would be a completely different animal. Clean aerodynamic lines replaced ornamental curves. A single vertical tail replaced the unstable twin-fin design that had plagued earlier prototypes. The wings were mid-mounted for optimal structural integrity and easier maintenance. Every bolt, every panel, every connection served a purpose, and nothing more. Most critical of all was the choice of power plant. Rather than modifying an existing engine, Matsumura argued for a clean-sheet design. The Nakajima NK9 Homar, a 2,000 horsepower radial built for altitude and endurance. 4 of these engines would give the bomber a combined 8,000 horsepower, a figure that finally brought Japan into the realm of American power-to-weight standards. But Matsumura's team didn't just copy performance figures. They copied philosophy. From the captured Wright Cyclone engines, they had learned that reliability mattered more than raw horsepower. Cylinder fins were simplified for mass production. Tolerances were relaxed just enough to allow faster machining, without compromising performance. Each engine was designed not for the ideal pilot, but for the average mechanic, a concept revolutionary to Japanese engineering culture. The airframe followed the same logic. Instead of the Shinzān's hand-forged spars and custom-machined fittings, the Renzān used extruded aluminum beams that could be produced in bulk on rolling mills. Reinforcement was concentrated only where stress demanded it. Panels were attached with accessible fasteners, designed to be removed or replaced with field tools. For the electrical systems, Nakajima engineers borrowed directly from the B-17's logic, color-coded wiring, standardized plugs, modular panels. No more handcrafted circuits or hidden cables. Now, even a half-trained mechanic could replace a system in hours rather than days. The fuel system showed the greatest philosophical change of all. Self-sealing rubber bladders replaced rigid tanks. Fuel pumps were standardized, mounted for easy access. Every valve could be replaced without dismantling the surrounding structure. The defensive armament layout was practical rather than ornate. Instead of complex hydraulic turrets, the Renzān used mechanical mounts that accepted multiple weapon types. The emphasis was no longer on elegance. It was on field performance, repair speed, and operational flexibility. By August 1944, the first G8N prototype rolled out of the Nakajima assembly hangar. The workers who had assembled it, many of them former craftsmen now retrained as production engineers, gathered around as the massive bomber gleamed under the factory lamps. To them, it was more than a machine. It was proof that Japan could still innovate. Test pilot Captain Takeshi Shirani lifted the Renzān into the air for the first time on October 23, 1944. His flight report stunned even the most skeptical officials. Top speed, 368 mph at 26,000 feet. Service ceiling, 33,400 feet. Operational range, 4,639 miles. For the first time in the war, Japan had built a heavy bomber that could truly rival American performance. It was on paper a triumph of engineering. But in the skies above Tokyo, the thunder of B-29 superfortresses told a different story. While Matsumura's team perfected a handful of prototypes, American factories were producing bombers by the hundreds every month. The aluminum that once fed the Renzān project was now being diverted to build fighters for Japan's crumbling air defense. By March 1945, only 4 Renzāns existed. They represented the absolute peak of Japanese aviation and the futility of perfection in an age of mass production. When surrender finally came on August 15, 1945, Matsumura stood in the engineering hangar beside the 4th G8N prototype. As Emperor Hirohito's voice came through the static of the loudspeakers, his engineers listened in silence, their faces illuminated by the metallic reflections of the bomber that would never fly in combat. Outside, American B-29s still crossed the skies, leaving contrails like white scars over the ruins of Japanese cities. They were the physical manifestation of everything Japan had failed to grasp, the idea that quantity had its own kind of quality. 3 weeks later, on September 3rd, Colonel Harold Watson and his American technical inspection team arrived at Kusumi. Their mission to examine Japan's most advanced aircraft and determine what the enemy had achieved. To Matsumura's surprise, the Americans showed no arrogance. They listened intently as he explained every detail: the design changes, the modular construction, the revised cooling systems. They took notes not as conquerors, but as fellow engineers. The Americans quickly saw what the Renzān represented: brilliance born too late. Watson's report, classified for decades, summarized the paradox in a single devastating line. Technical excellence without industrial capacity is strategically meaningless. The data his team collected confirmed that truth. Each G8N required 42,000 man-hours to manufacture. A single B-29 required less than 18,000. Each Renzān consumed 8.7 tons of aluminum, compared to 6.2 for an American bomber. Japan's total aluminum output in 1944 was about 142,000 tons, enough to build 16,000 bombers only in theory. America's production in the same year exceeded 900,000 tons. That difference wasn't just numbers, it was destiny. Even the engines told the same story of imbalance. The NK-9 Homer produced 2,000 horsepower but needed a major overhaul every 120 hours of flight. The American Wright R-3350 Cyclone produced 2,200 horsepower and could run for 400 hours before service. Where Japan sought perfection, America had mastered reliability. The Renzān's wing spars were machined from solid billets of aluminum, perfect in strength, disastrous in efficiency. The B-29's spars, by contrast, were built from extrusions and stamped parts, mass-produced by semi-skilled workers. The American parts were not better, they were enough. Maintenance logs revealed an even harsher reality. A G8N required trained mechanics, specialized tools, and days of downtime for repairs. A B-29 could be serviced by field crews in hours, using common wrenches and interchangeable parts. That difference, not speed, not altitude, decided wars. By November 1945, the 4th and final G8N prototype was loaded aboard an American transport for shipment to Wright Field in Ohio. Matsumura stood on the tarmac, his coat whipping in, the wind watching his creation vanish into the gray clouds. He felt pride, and an emptiness that no technical achievement could fill. He had built one of the most advanced bombers of the war. But the war had already decided what mattered most. Not brilliance, but scale. 4 years of work, 4 aircraft. An achievement unmatched and irrelevant. Later that winter, when Matsumura was interviewed one last time by Colonel Watson, the conversation turned philosophical. Neither man spoke of politics or victory. They spoke instead of arithmetic, the cold industrial mathematics of total war. Watson's final report summed it up with brutal clarity. Victory does not belong to those who build the best weapons, but to those who can build enough of them. Japan had finally learned how to build airplanes the right way, simple, reliable, efficient. But by the time it did, its factories lay in ruins, its cities burned, its empire dissolved. As the last Renzān disappeared into American custody, Matsumura looked across the airfield and saw the future. A future defined not by craftsmen, but by production lines. The lesson of the Renzān would live on, not in Japan's wartime glory, but in its post-war rebirth as an industrial power that finally understood the balance between precision and production. The G8N Renzān had been born too late to change history, but not too late to teach it. Subscribe for more untold stories of the machines, minds, and moments that changed World War II.